Hello, calculus friends. Today we are going to talk about the derivatives of the trig functions, and you do need to get these memorized as soon as possible. They're not going anywhere. It's not like, oh, we're going to do trig and then never look at it again. We do lots of trig. So make sure once we get to the derivatives here that you memorize them as quickly as you can. That should not be an impossible feat, but this isn't one of those where you're like, I'll get around to it. No, seriously, learn them. So in order to get to these derivatives, what I want to do right now is prove to you algebraically where they come from, so they don't just come out of thin air. Now, in order to prove where the derivative comes from, we actually need to remember two limits. The limit is x approaches 0 of sine x over x, and that's 1. And then if x approaches 0 for 1 minus cosine x over x, that one goes to 0. Now, why did we need to know that? Because what I'm going to use is I'm going to use the limit definition of the derivative in order to algebraically find the derivative of sine x. So the limit definition of the derivative is the one that says the limit, f prime of x is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. Okay, limit is f of x plus h minus f of x all over h, because that's really delta y over delta x. So if I want to find the derivative of the sine function, I'm going to call the sine function f of x. So if I want to take the derivative of sine x, I would say that f prime of x is equal to the limit as h approaches 0 of sine x plus h minus sine x all over h. But if I plug in h goes to 0, I have sine x minus sine x over 0. I have 0 over 0. I can't cancel anything out. I'm really stuck right now. So what we get to use is the sum and difference formulas for trig. And I don't know if any of you really remember these, or maybe you might not have learned them. I don't even know. So we're going to go over them. There are two sum and difference formulas. The sine of a plus or minus b is sine a cosine b plus cosine A sine B, and the cosine of A plus or minus B is cosine A cosine B, I forgot to write plus or minus, minus plus sine A sine B. What? Okay, so what that really says is the sine of A plus B would be sine A cosine B plus cosine A sine B. If that was a minus, then there would be a minus over there. For cosine, when you're adding two angles, you can do the cosine of each angle minus the sine of each angle, okay, or the reverse. And if you're wondering, how do you remember that formula, Mrs. Vibber? I have a song for that. I feel like, who is that? Tamatoa, okay? I will gladly do so in song form. Sine, cosine, cosine, sine, cosine, cosine, sine, sine, sine. The best way to remember this formula. God, I love that. Sine of a plus b, cosine of a plus b, sine, cosine, cosine, sine, cosine, cosine, sine, 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 because you change the sign in the middle. Yay, it's so cool. I love this formula. So how does that help us over here? Well, I'm adding some stuff within a sine function. So I am going to rewrite this in a different form. I'll go back to black so these fit here. And I have the limit as h approaches 0 of sine, cosine, cosine, sine. And then I still have that minus sine x, which is fine. And that's all over h, which is fine. And this really didn't help me any, because if I plug in 0 for h now, I have sine x times cosine 0, which is sine x. Then cosine x times sine h, and the sine of 0 would be 0, so this would disappear. Then minus another sine x. I still have 0 over 0. So this wasn't that helpful. Well, I have a bunch of things here where I have a sine x here and I have a sine x there. So what I can do is rewrite that in factor form and have the limit as h approaches 0 of sine x times cosine h minus 1 plus cosine x sine h all over h. Okay, so what I did is I pulled the GCF of sine x out of the first and the last term, and then I just kept the middle term the way it was. And then just to save a little bit of space, what I'm really going to do with this is I'm going to split it into two fractions here. Let's see if I can do it without disappearing everything. I did it. If that's all divided by h, technically each of these is divided by h. Okay, Remember that really bad joke I told you about setting the dumpster on fire? We're going to set the dumpster on fire here. We're going to take this and we're going to break it down to a previously solved problem. I am going to rewrite this as the limit as h approaches 0 of sine x times cosine h minus 1 over h plus the limit as h approaches 0 of cosine x times sine h over h. I can do that. And then I'm going to realize as h approaches 0, this limit is this one from up here. So this limit equals 0. Sine h over h, as h goes to 0, is the limit in the top left. So that goes to 1, and cosine x times 1 is just cosine x. Sine x times 0 is 0. So we finally get that cosine x is the derivative of sine x. Holy cowabunga, dude. That's where the algebra comes from. Now, I can also show you this graphically. So if I want to do this graphically, and I have a little bit of space right here. Now, graphically isn't a proof of why the derivative of sine x is cosine x, but it is a very visual justification. So if I have the graph of sine x, which is f of x, and I want to draw the graph of f prime, whenever f has a relative extrema, or whenever f has a slope of 0, f prime has an x-intercept, and f is increasing before that and decreasing after and then increasing. I have to increase, decrease, increase, and now I have the derivative. I have f prime, and if you look at that f prime definitely looks a lot like the graph of cosine, okay? But in the end, you need to know that the derivative of sine is cosine. Yay, awesome. You could prove that the derivative of cosine is equal to negative sine using the same limit method and the same limits as above. I'm not going to go through and do that again, just trust me, because cosine has a sum and difference formula like this. I could do the same exact thing to prove that the derivative of cosine is negative sine. Now, what about tangent? Well, if I want to find the derivative of tangent, I can use sine and cosine in the quotient rule, because tan x is equal to sine x over cosine x. That means the derivative of tan x is equal to the derivative of sine over cos. So now let's take the derivative of tan using the quotient rule. So I would have low d high, the derivative of sine is cosine, minus high d low, the derivative of cosine is negative sine, all over low times low, which would be cosine squared. And then on top, I have cosine times cosine minus negative, so that becomes plus. Cosine times cosine plus sine times sine, which is cosine squared x plus sine squared x all over cosine squared x. Anybody remember their Pythagorean identities? I do. Sine squared x plus cosine squared x equals 1. And so the derivative of tan is 1 over cosine squared, but because we don't like doing calculus on fractions when we don't have to do calculus on fractions, 1 over cosine squared is the same as secant squared. Remember the reciprocals for sine, cosine, and tangent are cosecant, secant, and cotangent? We're going to need to know those too. All right, so in the end, if you are like, I don't know what just happened, you do need to memorize these derivatives. I'd really like you to not be head exploded right now, but you need to know that the derivative of the 6 trig functions are down here. The derivative of sine is cosine. The derivative of cosine is negative sine. The derivative of tangent is secant squared. All the ones on the bottom you can get by taking the quotient rule and using the reciprocal on top. So if you want the derivative of cosecant, you can take the derivative of 1 over sine and use the quotient rule. If you did that, the derivative of cosecant is negative cosecant cotangent. The derivative of secant is secant times tangent, and the derivative of cotangent is negative cosecant squared. You will notice that 3 of these functions start with the letter c, and every function who starts with the letter c has a derivative with a negative sign in front of it. So if you're wondering, how am I going to remember which ones are positive and negative? If it starts with c, the derivative should be negative. Okay? Okay. Now let's go on to the back. For examples 1 through 7, find the first derivative. Okay. X squared times sine x. Now we need the product rule. All right. And this is really the first time in the course that we've needed the product rule. All the other times we've done the product rule, we could have gotten around it by like distributing and then using a power rule. Like if I had you multiply x times x squared plus 3, you could do the product rule, but it makes a lot more sense to like multiply it out first. All right. Now I can't multiply out x squared times sine x. It's not going to happen. So instead, I have to use the product rule. When your product is 2 different types of functions, you are stuck. Product rule it is. So I need to take the derivative f prime of x, and I'm going to do it just using the rules that I memorized from the front page. And I put memorized in quotes because I know you're not there yet. I am, because I'm paid to be there. All right, f prime is the first times the derivative of the second. The derivative of sine is cosine, plus the second times the derivative of the first. The derivative of x squared is 2x. Please make sure you know that sine x is being multiplied by 2x, not x times 2x, which gives me f prime of x equals x squared cosine x plus 2x sine x. Da-da-da, yay! And we're done. Example 2, 5 secant x plus tangent x. Don't need a product rule here. So since it's written as y, I'm going to write the derivative as dy dx. If my original function is written in function notation, I'm using the prime. If my original is written as y equals, I'm going to write the derivative as dy dx. The derivative of 5 secant x, well, the derivative of secant, flip to the front, was secant tangent. So the derivative of 5 secant is 5 secant tangent. And then the derivative of tangent is secant squared x. If you want to, you could factor out a secant, but there's really no reason to do that. We can just write it like this. Done. Example 3, cosine x divided by x. All right, cosine x divided by x, that's a quotient. I need the quotient rule. G prime of x equals low d high, the derivative of cosine is negative sine, minus high d low, all over low times low. And so g prime of x is negative x sine x minus cosine x, all over x squared. Okay. Fun fact, because mathematicians like to deal with as few negatives as possible, you will often see us pull this negative out in front of the entire fraction and write it as x sine x plus cosine x all over x squared. Each of those is equivalent. Or pull the negative down to the x squared. That happens sometimes too. Now, I don't want to keep going in this video because we're already probably at close to 15 minutes. So what I want to do next is just show you how to check these in Desmos, and then I'm going to pause my video, quick write out all the rest of the answers. You're going to pause your video, figure out the rest of the answers, and then match up and see if they fit. Okay, now before I do that though, I want to show you how to check, because then you technically don't need to look at mine because you'll know if you're right. I'm going to go to my favorite place in the world, which is Desmos. Okay. Oh, I wonder what the Google Doodle is about today. I'll have to figure that out later. All right. So in Desmos, I am going to write f of x equals x squared sine x. Oh, you know what I forgot to say? I forgot to say this. You are in calculus. You are in radians. Full stop. Okay. Derivatives of sine x in radians are different than the derivative of sine x if it's in degrees. Okay, so know that. Everything we do is in radians, and when you use Desmos, it defaults to radians. Thank you, Desmos. So radians only, radians. Get in your calculator, change your mode to radians when you are in calculus. I know in physics you have to be in degrees, but for me, radians. Okay, end of story. So here is the graph of, wow, that's fun. X squared sine x, that's kind of cool. And if I want to know what the derivative looks like, I can literally just type f prime of x, and it graphs the derivative. That's cool. Now, if I want to know if my graph is the same as that f prime graph, I'm going to come back over here and type y equals x squared cosine x plus 2x sine x. And then I can turn this on and off. There's the blue, there's my green, and they are exactly the same. Yay. So I know I got my derivative right. Cool, cool, cool. And then we can do that for the other ones also. I didn't mean to delete that. I'm going to change this instead of to x squared sine x to 5 secant x plus tangent x. All right. So there's my original. Okay, the red one's my original. The blue one is my derivative, or pardon me, the calculated derivative. Now I'm going to type in my derivative in number 3. 5 secant x tangent x plus secant squared. 5 secant x tangent x plus secant squared x. Blue graph, green graph. Blue graph, green graph. Yay, we got it right. All right, so pause your video. Do examples 4 through, I don't know, what does it end? 8. And then unpause your video and check yours with mine. How do I pause my thing? Pause my video. It's over here. Pausing. Hello, we're back again. So now let's go over those answers that hopefully you got. I'm going to talk through them, but I'm going to show the answers first. So for example 4, your answer should be negative theta to the negative 2, or negative 1 over theta squared, plus 4 cosecant theta, cotangent theta. Number 5, 1/2 x to the negative 1/2, plus 3 secant squared. Number 6, secant cubed x plus secant x times tangent squared x. Number 7, negative 2 secant minus 2 sine cos. And then number 8, the final answer is a negative sine. If you got all those right, you're good to go. If not, take a moment and listen to me explain them. Or if you got them right, listen to me explain them anyway, because you still got to wait for the joke. All right, so bounce it back up. On number 4, one of the things you have to realize here is I can use whatever variables I want. R equals 1 over theta minus 4 cosecant theta is the same as y equals 1 over x minus 4 cosecant x. Same thing. Okay, so when I take the derivative instead of dy dx this time, it's dr d theta. And so then I just thought, well, theta's to the negative 1 minus 4 cosecant theta. The derivative of theta to the negative 1 is negative theta to the negative 2, power rule. And then 4 cosecant theta, 4 is a lead coefficient. So what happens with that is it just kind of waits out in front. So the derivative of cosecant is negative cotangent squared. The derivative of cosecant is negative cosecant cotangent. My apologies. So when I take the derivative there, it becomes plus cosecant cotangent, and the 4 just comes back. All right, now number 5, this one, pretty straightforward. 1/2 x to the negative 1/2, and the derivative of tangent is secant squared, and the 3 just stays in front. Number 6 is secant times tangent, so I need the product rule. The first times the derivative of the second plus the second times the derivative of the first. Now, you can leave it like that, but it's begging to be simplified. So secant times secant squared is secant cubed. Tangent secant tangent is secant times tangent squared. Okay. Again, unsimplified is okay. Simplified is way better. Then I come down here to number 7. I wanted to talk about this one. So we have this lead coefficient out in front, and you kind of have 2 options here. I have 2 times cosine times cotan. So I could do this as 2 times the product rule and then distribute the 2 later. I can also do it the way that I have it written out right now, whereas in my head, when I do the product rule, I think of 2 cosine as the first part of the product and cotan as the second part of the product. So there's the first times the derivative of the second plus the second times the derivative of the first. So I kind of attach the two to the first part of the product. Then I realized cosine times secant is 1 over cosine. So cosine times secant actually cancels out one of the secants. So this becomes negative 2 secant t minus 2 sine t cosine t. Okay. And then last but not least, on number 8, it says find f14x when f of x is sine x. When you see what looks like an exponent, but it's in parentheses, that actually means the 14th derivative. This is a notation you haven't really seen before. Usually we use like apostrophes in the beginning, and then once we get to 4, we start putting it in parentheses because nobody wants that many apostrophes. So if I start with sine x, the derivative is cosine x. The second derivative would be the derivative of cosine, which is negative sine. The third derivative, negative cosine. The fourth derivative, I'm back to sine. So it's a lot like the I cycle where this goes through in 4s. Cosine, negative cosine, sine. Boom, 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 boom. So if I want the 14th derivative, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, I'm at negative sine x. And there's always a joke at the end, and it's October, so your joke for today is Halloweeny. Why doesn't Dracula have that many friends? Kind of sad. Why doesn't Dracula have that many friends? He is a huge pain in the neck. All right, everybody. Have a good one.